Hi everyone, and welcome to the third session of the PyBAM training workshop. In this session we're going to focus on parameterization, and in particular we're going to see how to manage parameter sets and add your own parameters, and we're going to see some applications and how you can tweak parameters to do data fitting and see how you can calculate sensitivities of the model outputs with respect to parameters.
Hi, so in this session, we're going to focus on the parameter management in PyBAM. But unlike what we saw in session one, that we imported the parameters and made some changes in them directly on the script, what we're going to do today is see how we can define a new parameter set. So basically, we make the changes directly on the parameter set, and when we import, it already has the parameters we want. And that's extremely helpful in those cases where we want to run multiple simulations with the same parameter set. Or we want to define a completely new parameter set, so we can do this once and then import the updated version instead of making the changes at each script. So before seeing that, let's look into how PyBAM stores the parameters. So if you remember from, let me import PyBAM first. If you remember from session one, we could import parameter values from the predefined parameter sets in PyBAM. So if I do PyBAM.parameter sets, then I can just call some of the default ones, in this case, Chen 2020. And that's basically a dictionary that points, it points to different components of the parameter set where to look at. So instead of defining one big parameter set, PyBAM does it in chunks. So there's going to be some cell parameters that include the cell geometry, some negative electrode and positive electrode parameters, and they're all distributed. And that actually matches on how PyBAM stores the parameters, because then basically when we process the parameter values, it goes to this dictionary and reads each component, each block from the corresponding file. So if actually you go where parameters live in PyBAM, which is in this input parameters subdirectory, I'm showing this on GitHub, but it will be the same if you just go and check where PyBAM is installed in your local machine. You'll see that there are two subdirectories, one for lead acid and one from lithium ion. These are the chemistries. And if you, for example, look inside of lithium ion, notice that there are different subfolders that match those the entries of the dictionary, like the different keys on the dictionary. And then the different parameter sets are stored in the corresponding subfolders. So for example, in negative electrodes, we have Chen 2020 here. We also have all the other parameter sets. So basically, PyBAM will go and collect the parameters from here. And if we check what's inside of this file, what we'll see is that there is this parameters.csv. That's the most important file here, because if we open it, what we'll see is that this is this CSV file that has all the parameter values. And the ways they're defined, some of them is very obvious. For example, negative electroconductivity, it's a value, it's 215. That's very straightforward. Now, the OCB, on the contrary, is defined by that. That looks a bit complicated, but basically there is this tag here in square brackets that says function, means that PyBAM will have to read a function, and then afterwards it tells PyBAM where this, how this function is called. So if we go to the previous folder, basically there is this function called graphite algem50 OCP chen2020.py, and if you look into it, this is just a Python function that imports the parameter that basically takes the stoichiometry and returns the open circuit potential. So when PyBAM reads the parameter, it's going to process this function and bring it in. There's another option that is, instead of doing square brackets function, do square brackets data and pass a CSV file, and then PyBAM will create an interpolant from that. And for example, if you want to check here, there is this CSV file for the OCV in case you want to define it from data. So here is the example. Now, having seen that, let's look where PyBAM looks for the parameters. So the way PyBAM looks for the parameters is through this parameter path variable. So we'll go through all the paths in this variable and search the parameters there. And it goes in order. That's quite important because it means that PyBAM will first search here, which is where PyBAM is installed. Then it will search on your current working directory. And then finally, we'll look for this, which is basically where PyBAM is installed, but the input parameters directory. And as I said, you could here add any other paths that you want, but that's quite important because PyBAM will go in order. So if PyBAM finds a parameter set in your current working directory, it will not go further, and this will override, or in terms of how PyBAM imports, the default values. But that's actually very handy because if you want to define new parameter sets, instead of overriding the ones where PyBAM is installed, that could be quite tricky and cause things to crash. What we can do is define them locally, and then PyBAM will import them from there. And we would need to define a folder structure. It's the same that PyBAM knows, with all the subdirectories. But instead of doing that manually, there is a routine that will do that for us. This routine needs to be run from bash, but we can do that directly from Jupyter Notebook, putting this line first. And then we do the command we want. In this case, it's pybam _edit _parameter, and we have to specify which chemistry, in this case, lithium ion. So if we do that, this will create a new file will appear here. So a new folder will appear here once it's finished copying. That is called lithium ion. And this will contain a copy of all the parameters. So we can now modify those parameters here. So as you can see, it has now updated. And there is this folder, which looks exactly the same as the one by default in PyBAM. So now we can create a new parameter set. And the best way to go is to just copy an existing one and modify it. In this case, what I'm going to do is copy the graphite Chen 2020 parameter set. Here I say the path, graphite Chen 2020, and I'm going to create one that it's just for the purpose of these workshops. I'm just going to call it graphite workshop. So now that I have this new parameter set, if we go in here, negative electrodes, notice that there is a graphite workshop, and I can just modify the parameter values as I want. You can do that on the text editor that you want. In particular, you could change all the parameters, but I'm just going to change one. And I'm going to set the diffusivity instead of 3.3 10 to the minus 14, I would say 5 10 to the minus 15. So I save this file. And basically, now I can import this new parameter set. To do that, I'm going to go via a chemistry. But in this case, I would have to find a chemistry for positive electrode, electrolyte, and so on. So I'm just going to start from an existing one again. This is the Chen 2020. So if we check the negative electrode, notice that it's graphite Chen 2020. But now I'm just going to change that and notice that this is just a dictionary. So I say for negative electrode instead, take graphite _ workshop. So again, if now we check the chemistry, this is the new one. So now if we go and import the parameter values, so let's do parameter values, and we import them as we learned in session 1 from this chemistry I just defined. Notice that if we now ask, okay, what's the value for the negative electrode diffusivity? It gives a new value, 5 10 to the minus 15. That's the one I put in, I modified. Now, you can now just go with this parameter set, run simulations. But the next step is like, what if I want to contribute this new parameter set to PyBAM for other people to use? Well, first you would have to fork the PyBAM repository and clone it into your machine. And then you would have to copy the new parameter sets you created into the right directory. Now, that can be a bit cumbersome if you do it manually, but luckily, there is another command from in bash that does that for you. So in this case, it's pybam _at _ parameter. So if we do that, we can just say which chemistry we want to copy. So in this case, we say the new parameter set, leaves it here in this path. And we want to copy it into lithium ion and then negative electrodes. So we execute this command, and this will copy the parameter set into the PyBAM, the ones that PyBAM has in the path where it's installed. And to check that works, what we will do is try to pull the parameters, but first we need to remove the local copy, because if we don't remove the local copy, as I said before, PyBAM goes in order, so we'll first search the local directory, and therefore we won't be able to see if it actually works. So I remove the local copy. As you can see here, now this is no longer here. There's no graphite _ workshop. And now I can just, I'll do another variable to import that to make sure we are not actually calling the previous one. So if we now do that and we import from chemistry, notice that that worked fine. And if we actually pull and ask, okay, what's the new parameter value? Again, is the one we modified, which means it worked. Now, just before finishing, let's see what happens if you want to remove a parameter set from the ones you have where PyBAM is installed, the kind of the default ones. So again, from bash, you can do pybam _rm _ parameter, and you specify the -f is to force it to delete it in case there are any conflicts. Which one you want to delete, which is this path, and we want to delete it from this subfolder, negative electrodes. So we execute that would delete it. And that means that if once that's done, if I try to import parameter values again, I get an error. And the error is that this parameter set cannot be found as we expected. So that is everything. Before finishing, I'll just delete the file I created locally with the parameters to leave everything as it was. So yeah, if we check here now, this file is gone and everything is as it was at the beginning of the session. So thank you very much for listening, and I'll be very happy to answer questions in the Q&A part.
Good afternoon. My name is Martin Robinson, and in this video, I'm going to be demonstrating how to use input parameters for a PyBAM model. So input parameters are similar to standard parameters in PyBAM, except that instead of that parameter being replaced by a specific value during the model setup process, an input parameter is kept as a symbolic parameter all the way up to when you actually solve the model. And this way you can vary one or more parameters that are input parameters of your model while solving it multiple times, rather than reinitializing the values of those parameters at each time. Okay, and so one of the applications for input parameters is to use them when you're fitting models to data. And so I'll demonstrate how to do that as well. Okay. So the first thing that we want to do is get the dependencies that we're going to use today, which I've already done. And then I'm going to first demonstrate the use of input parameters with a toy model. Okay, so I'm going to create an empty model. Just going to call it name. And we're going to create a state variable y and also a parameter which we're going to call a. And then we're going to give an equation for our model. So we're going to set a single right-hand side equation, which is dy dt equals a times y. And in this case, we're going to need some initial conditions as well. So we're going to set y equals 1. Okay. So once we've created our model, we can do things like inspecting the right-hand side equation, which is just a times y, as we specified above. And what we'd often do now is use the parameter values class in PyBAM to set specific values for those parameters. Okay, so here we're going to create a parameter values object, and this parameter values object contains a single parameter a, which is given a value of 2. And then we can use the process model function of parameter values to actually go through the model and replace all parameters, all a parameters with 2. Okay, so if we print out our right-hand side equation again, then we can see that our parameter a is being replaced by 2. Okay. So once we've done this, then we can just go through the standard process of creating a solver. In this case, we're going to use the Casati solver, get an array of times to evaluate the model at, and we're going to solve the model using the solve function in the solver, and then we're going to plot the solution. Okay. When we do that, we get a solution as we expect. Okay. So now we're going to do the same thing, except we're going to use an input parameter. Okay. So we create our model again with the same variable y, and now we're going to use an input parameter rather than a standard parameter. And we're going to create our right-hand side equation. We're going to create our initial conditions, just like before. And once again, we're also going to create a Casati solver object and get an array of time values. But now, because we've got an input parameter in our model, we can actually start to vary that parameter over a number of different values and solve it without reinitializing the model again. Okay, so we're going to create a loop here varying a from 1 to 5, and at each iteration of that loop we're going to use our solver object, and we're going to call the solve object again, but now we're going to pass in an additional keyword argument called inputs. And we're going to give our value for A here. Okay. And once we've got our solution, we're also going to plot that out. Okay. So the first time you call solve on this model, the solve goes through and sets up all the things it needs to do to solve that particular model. Okay, and that involves a non-trivial cost. Okay, so you want to avoid setting up models over and over again. And what our input parameter allows us to do is call solve multiple times, but it's only on the first evaluation of solve where the model is set up, and subsequent solves there's no setup process, so it can just solve the problem. So it's a much more efficient process. Okay, so we're going to plot. We're going to evaluate a loop which plots our solution, and you can see that we've evaluated our model using different values of A, and gotten the results and plotted them over on top of each other. Okay. So often you're going to already have a model in place which uses one or more pybam.parameter objects. So this would be the case if you're using one of the battery models that are provided by pybam, like the DFN model, for example. Okay. So in this case, what you want to do is take the existing model, which contains pybam.parameter objects, and convert the ones that you want to vary into input parameter objects. Okay. So you can do that with the parameter values class as well. Okay, so I'll quickly demonstrate this. So we're going to set up our toy problem again, but now we're going to use just a standard pybam.parameter object for our parameter A, and then we're going to create a parameter values class. But instead of setting A to a specific value, we're going to set it using this string here, which is open square brackets, input, close square brackets. And so what this will do is replace the parameter in the model here with an input parameter. Okay. So once we've done that, then we can go through the exact same process that we did before, creating a solver, creating an array of time values, looping through our different values of A, and then solving the model using those values and plotting the results. So once we do that, then we get a plot which looks exactly the same as before, although maybe a little bit prettier with the legend there. Okay, so this was using input parameters using a toy model. But obviously you're going to want to use one of the battery models within pybam, and so I'll quickly demonstrate how to do that. It's a very similar process. So the first thing we do is create our DFN model, and we're just going to use a few defaults. So for the geometry, we're just going to use the default geometry, and we're going to start off using the default parameter values as well. Okay. So this is going to give us all specific values for every single parameter in the DFN model. Okay, but what we want to do is convert one of those to an input parameter. And so we just like before, we use the update function on the parameter values class and replace a certain parameter, in this case the current function, with an input parameter. And then once we've done that, then we can use our parameter values object to first process the geometry and then process the model as normal. Okay, so what this will do is for most of the parameters in our DFN model, it's going to replace them with whatever values were in this default parameter values, except for the current function, which is going to replace with an input parameter. Okay, so we can run that. And then we can discretize the model. So I won't talk too much about this because this is just as normal, really. We just sort of discretize using our default mesh and set the number of points. Okay, so processed our model fully, and now it's ready to be solved. Okay, so we create our array of time values and our solver as well. In this case, using the Casati solver. And then we can solve the model using a specific value for our current function. In this case, we're just using 0.15652, which just so happens to be the default value anyway. Okay, so we solve our model like this, and then we can plot our result using the quick plot functionality in PyBAM, just as normal. Okay, so we plot this, we can see our result like this. Okay, but obviously we don't want to solve our model just once. We want to solve it many different times using different values for the current function. So we can set up a loop just like we did before, and this loop is going to look something like this. So we're going to vary our parameter between 0.1 and 0.5, and at each iteration of this loop, once again we're calling solver.solve, and we're going to pass in a specific value for current function a here. And once again, it's just the first evaluation of solve where the model is being set up and processed in preparation for solving it. So we don't have to go through, for example, we don't have to go through the discretization or the processing of the geometry, processing the model. And there's other things that the solver needs to do to set up the model to solve it efficiently, which it only does in the first iteration of solve. But subsequent iterations of solve, it's not going to need to do any of those things. So you avoid a lot of the setup costs. Okay, so we're going to plot that, and then we get something which looks like this. So here we're just plotting the terminal voltage. Yeah, so we're just extracting our terminal voltage from our solution and plotting that. And so each of these lines is the terminal voltage solved at a different value of the current function. Okay. Okay, so I mentioned at the beginning that one of the applications of using an input parameter is for a parameterization and data fitting. So let's construct a toy example of this sort of data fitting process, again using our DFN model. Okay, so the first thing we need to do is generate some data, obviously. And so for data, we're just going to use a simulation to generate some fake data. And we're going to, once again, we're going to use the terminal voltage output, and we're going to use the specific value of the current function, which is 0.2222. Okay, so that's our data that we're going to be fitting against. And so the first, once we've got our data, then we need to set up our optimization process. Okay. And here we're just going to use a standard sort of sum of squares objective function. So we're going to aim to minimize the sum of squares distance between our simulation and our fake data in order to recover the original value of the current function. Okay. So first thing we need to do is set up the function to optimize. And so this function is going to take a vector of parameters, so which only contains the value of the current function. And at each iteration, at each evaluation of the function, it's going to solve our DFN model using that specific parameter. Okay, so we're passing in this parameter that we got from our parameters vector into our inputs keyword argument of the solve function for our solver, and we extract the terminal voltage. Okay, and so that gets our simulation, and then we can write down our sum of squares objective function like this, which is just our simulation minus our data that we got up here, all squared, and then take the sum of that array. Okay, so that's the function that we want to minimize in this case. And to do the actual minimization, as I said, we're going to use the SciPy library. Now there's a few practical things we need to do to actually do this minimization. First thing is that you want to place bounds on the parameters. Okay, so you want to do this because depending on the optimization, the specific optimization algorithm, it could try to solve our DFM model at a variety of different parameters. And some of these might not be, might lead to a model which is impossible or difficult to solve numerically. Okay, so for example, a lot of the parameters, it wouldn't make sense for them to go negative. Okay, you wouldn't be able to solve the model in that case. Or other values for the parameters might result in the simulation terminating earlier due to the events in the model, which would be unexpected and would cause our sum of squares function to fail in that case. Okay, so we want to put some bounds on the parameter. And in this case, we're going to place bounds varying from 0.01 to 0.6. And in most optimization algorithms also require a starting point as well. And we're just going to use a random initial starting point somewhere between our two bounds, like so. Okay. So once we've got our bounds and our starting point, then we can actually do the optimization. So we're going to use the minimize function in scipy.optimise. And this takes a function to minimize, which is our sum of squares function here. It takes an initial condition, or a vector of initial parameters, which we're going to set here, and also takes some bounds as well, which we're going to pass in there. Okay. Now once we've done that, then we can see we're starting from 0.39. And then the optimization algorithm continues all the while sort of evaluating our sum of squares function until it gets to a solution, which is quite near the value that we use to generate the data. Okay, so just to remind you, the value that we used to generate the data was 0.2222, and we got quite close to that here. Okay. So that's an example of using input parameters and data fitting. And so in the next video, I'm going to demonstrate PyBAM's functionality in terms of evaluating the sensitivities of the model and how you can use that for data fitting as well. Okay, good afternoon. So in the previous notebook, we used an PyBAM.input parameter to enable us to run many simulations with varying parameters. So in this video, we're going to demonstrate PyBAM's abilities to calculate the sensitivities of model outputs with respect to the input parameters. Okay, so here we're basically trying to calculate the partial derivative of our model outputs with respect to our input parameters. Okay. So we're first going to demonstrate this using the same toy model that we used before. Okay, so this is just going to look like this. We construct an empty model using PyBAM.base model. We add a variable and an input parameter. We set up our right-hand side equation and our initial conditions. Although in this case, now we're going to define a model output as well, which is simply going to be y squared. Okay. So we're going to define that like so. And then we can create a solver. In this case, it's a Casati solver and a vector of time values that we want to solve that. And then we can solve our model. But in this case, as well as actually generating the solution of our model, okay, so as well as trying to calculate the values of y and to get a simulation object, we're also going to calculate the sensitivities of our model. Okay, and we're going to do that by using the calculate sensitivities keyword argument to this solve function. Okay, we're going to set that to true, and what that is telling the solve function is that we want to calculate the sensitivities to all the input parameters of our model. Okay, so we've only got one input parameter. It's A. So it's only going to calculate the sensitivities with respect to this parameter A. Okay, so we could have also passed in a vector of input parameters that we wanted to calculate the sensitivities for as well, but setting it to true just gives us a shortcut in this case. Okay, so now we've solved our model, and our solution object now contains both the solution of the state variables as well as the sensitivities for those state variables with respect to our input parameter A. Okay, so we can start plotting this. Okay, so what I'm going to do here is I'm going to create two plots, and on the first plot I'm going to plot y squared. Okay, I'm going to give it labels as well, and in the second plot I'm going to plot the sensitivities. Okay, so we can get the sensitivities from our solution object by first specifying an output. Okay, so in this case we're looking at y squared, and then we say dot sensitivities, and we give the parameter that we want the sensitivities with respect to. Okay, so here we're extracting the partial derivative of y squared with respect to A. Okay, I evaluate that, and we get both plots of y squared here and the gradient of y squared with respect to A. So this, if you can see that here, this is dy squared dA. Okay. Okay, so that's the sensitivities for a toy model, and I just want to demonstrate that you can do the same thing with the battery models that exist in PyBAM. Okay, so we're going to once again use the DFN model. Use the default geometry and start off with the default parameter values as well. So remember, we need to convert one of our parameters to an input parameter. And here we're going to once again pick on the current function parameter. We're going to convert that to an input parameter, and then we're going to process the model using our parameter values class like this. And then we're going to discretize our model and create our solver. Okay, so this is just discretizing, and this here is just creating the model. Okay, and we can now evaluate the sensitivities of any of the outputs of this model with respect to our input parameter current function. Okay, so we're going to use our solver, and we're going to solve the model. We need to provide a value for the input parameter, obviously, which we do here. And we're going to say that we want to calculate the sensitivities of the model as before. Okay, so we evaluate that. So now we've got a solution object here. And so let's just plot this. Okay. So once again, we this is again demonstrating how to extract those sensitivities. First, you input the terminal voltage, so the output that you want the sensitivities of, and then you say dot sensitivities, and you give the input parameter that you want to calculate the sensitivities with respect to. Okay. Then we can just plot this, and we get something which looks like that. Okay, which is just saying that the which is probably fairly intuitive. That later time values your output, the terminal voltage is more sensitive with respect to that particular parameter. Okay, as you would expect. Okay, so I mentioned before that you can use sensitivities for data fitting as well. So I'm going to demonstrate this. And we're going to use the same. We're going to set up the same data fitting exercise as we did in the previous video. So first, we're going to generate our data here, and at a certain value of the current function, which we do like this. And now we want to set up the function that we want to minimize. Okay. And we're going to take advantage of certain features of the scipy.optimise library, and we're going to create a function which will return both the value of the function and its gradient with respect to the input parameters, input parameter vector. Okay. And so this function looks fairly similar to what we had before, so we're going to call it sum of squares jack. And we're going to, within that parameter, within that function, I should say, we're going to solve the model, but we also want to calculate the sensitivities of the solution as well. And then we're just going to extract two things from our sim solution here. We're going to extract the terminal voltage, okay, which is just done like this. And we're going to extract the sensitivities of the terminal voltage with respect to our input parameter A. Okay, so we got sim in brackets terminal voltage dot sensitivities, and then the parameter that we want, current function here. Now, after we do that, then we can actually start to write down the functions that we want to minimize. And the first one is just our sum of squares, as we had before. So just the difference between our simulation, which is given in term voltage, and our data, which we've got up here, all squared, and take the sum. And the second thing that we want to calculate is the gradient of f with respect to our input parameter current function. Okay. So if you consider this line of code here as a function, okay, so you have a sum over term voltage minus data. So the only thing in this function which depends on our input parameter is term voltage here. So if we take the gradient of this function here with respect to current function, you get this function here. So you've got 2, because you've got the square there, so 2 times the sum of term voltage minus data multiplied by the derivative of term voltage with respect to current function, which is our term voltage sends like that. Okay. And once we've got those two, we're just going to return them. Okay, so we're returning both f and g. Okay. So this is our objective function defined. And once again, we're going to use SciPy to optimize. And as we did before, we're going to need bounds, and we're also going to need a starting value. So we use the same bounds as we did before. So current function varying between 0.01 and 0.6, and a starting value randomly between those two bounds. And then we call our optimization algorithm, which is just the minimize function in SciPy.optimise. And we give it our sum of squares jack function, our starting parameter values, and our bounds. And then we use the jack keyword argument and set that to true. And what that is doing is just telling minimize that our sum of squares function here is returning both the value of the function and its gradient. Okay, so minimize will be able to use that gradient information to perform a more efficient minimization process. Okay, so evaluate that, and so we've got a starting parameter. It starts evaluating sum of squares jack function, and it gets fairly quickly to the result. Okay, we actually started fairly close to the result there, so we can try and run it again and get different starting value. So you can see that each evaluation of this function is taking more time than in the previous video, because we're calculating the sensitivities as well, which is more expensive. But it also takes less iterations to arrive at our solution. So it's a bit of a trade-off there. Like in some models, particularly those where you're fitting a large number of parameters, using the sensitivity is going to result in a more efficient process. But in other cases, maybe when you've only got a small number of parameters, or it's a particularly large model, for example, then it's probably not going to be more efficient to use the sensitivities. But having the sensitivities there gives you the option anyway. Okay. Thanks a lot for your attention, and yeah, I'll talk to you soon for questions. Thanks.
Thanks very much for joining us for this session. As always, there's a number of different ways you can access support with PyBAM. You can get in touch on our Slack channel, where we've got a very active community who can help out with any issues you might be having. You can go over to our GitHub page where you can create issues or discussions, and we also host implementation sessions, which are one-on-one or group sessions where you can workshop your ideas and ask for help about how you might go about doing something in PyBAM. For further information, you can go to our website, pybam.org. If you head to the contact page there, you can find our email address, and you can also request an invite to our Slack channel. You can also follow us on Twitter at pybam_. To show your support for the project, head over to our GitHub page and start the repository. And you can also try all our examples online via Google Colab. Thanks very much for joining us, and hopefully we'll see you all again in the session tomorrow.